Hello, my name is Simon Tracer. It's pretty late at night right now, but as usual, I end up watching a science video and I end up with a little tidbit of information that I disagree with wholeheartedly because it's fucking not true. So, what is this tidbit of information? The title should make it pretty obvious. Heisenberg uncertainty principle, lazy science. I've already stated in a previous video, but if you haven't seen that, let me say it again. A electron, when I looked it up, goes at 2,200 kilometers a second. What does that really mean? To put it in perspective, that's 2.2 million meters per second. Does that seem familiar? That's because light speed is 300 million meters per second, give or take. So basically, going at near 150 times this faster, you have light, and then you have the electron at its speed. Now, what is that speed relative to the atom that it's orbiting? Well, I did that math too. I found out that the atom is basically, well, majority case, 10 to the 10th meters. Nanometers, right? So, is that the correct way to say it? Wait, hold on. Okay, I wasn't wrong. It's 10 to the 10 to the minus 10 meters. In other words, it is that 10 billion? 1/10 billionth of a meter, right? Or 0.1 nanometers. So what does that really do to our electron's speed? Well, when you take the speed of the electron, which is in millions, and then that's 10 to the 6, or is it 10 to the 7? Correct me in the comments. But the point is, you take 10 to the 10th and 10 to the 6th, and then you add those together. You end up with the total ratio is an electron is moving 10 to the 16 of its own size of the size of an atom per second. 0.01 nanometers per second. So what is that really? Well, okay, no, that's not how it is. It's 2.2 times 10 to the 16. .1 nanometers per second. So the point is, at the size of a atom, there are why am I bad with math? 10 to the 16, isn't that quadrillion? 10 quadrillion spaces that the electron can be at all at the same time in 1 second. That's why when we look at them, we see a cloud. The basic diagrams that people end up seeing when they see electron patterns is all the spaces that they could possibly that they are occupying in a single second. Now let's pretend that instead of an electron, you're working with cars, and instead of 1 second, we say it's in the span of 10 minutes, and they're moving at whatever speed you want to think about. But you speed that footage up to the point where it's as fast as an electron. Yeah, if you could have basically think about a regular roundabout, right? You know, one of those English things where you go in circles and it's like the four-way stop or whatever, but it's a circle or five-way, whatever you want. So you got those roundabouts. Now pretend that you simulated what it's like having the car be seen on footage in ten quadrillion places. So, like, I don't know, let's say that that each frame of its movement is like, I don't, just try and visualize. The car is basically just, you sped up that footage so much that it's a blur, right? The only way that you would be able to see it in that roundabout in so many spaces is if you went for like decades constantly driving in that circle. One electron would be in that many spaces in 1 second of footage would seem like a complete blur, and it could go in and out of its normal area, and it could veer a little bit depending on how the driver is doing. He's not a perfect driver. He won't go in a complete circle every time. He's not a robot. She's not a robot. Whatever. And even robots have the ability to have a bit of variance, so it's going to be moving a little bit, and you'll end up with a big blur of this car. This is what's happening on the quantum scale. So when I see people talk about Heisenberg uncertainty principle, and they say it's impossible to predict, I say you're not fast enough. The moment you get a ability to be able to visualize the electron in that amount of space, first of all, like, let's say that you were able to see the electron moving at one instance every 1/30th of a second, right? So basically divide a quadrillion still so that you would see it would be circling like 10 times still right? It's 160th the speed of light. That's nothing to sniff at. That's going very fast in a very small area. So that's why electrons seem to be a blur. And it's not uncertainty. Not at all. There are ways of simulating the electron and how it moves, how it would orbit normally. And the reason that when I saw this video, okay, when I saw this video, they talk about superconductive stuff and electrons forming pairs.
Is where we more or less expect a particle to be. Its true position can never be known with 100% certainty, so the best approach is to imagine.
Okay, that is 100% a lie. That's just 100%. That is a complete, like, blank-faced lie. I don't know if bald-faced lie is the correct term, really, but like, you can know where the electron is at any given time if you have something capable of slowing down time fast enough and visualizing the electron without interfering with it somehow, right? If you can do that in any way at all, it's possible you can know where the electron is at any given time and how it actually... Now, the problem is, I originally commented simply no, because they mentioned the Heisenberg uncertainty principle, and I am diametrically opposed to that principle. It doesn't work like that in reality. It's not... And the other thing that I'm pissed off about, she says sometimes they work like waves.
Temperatures is the Bose-Einstein condensate. But first, there's a couple more things you need to know about quantum physics. In classical mechanics, we like to imagine particles as tiny little balls that interact with each other, but this is not what quantum physics tells us. Because of the uncertainty principle, it's not.
Okay, no, they are actually. That's the problem. An electron is a tiny little bar magnet, basically spheroid. It has the electromagnetic field flowing in a torus around itself, and it's orbiting the nucleus of the atom based on the attractiveness of the protons, and the amount of pull is always slightly different depending on what part of the proton it's orbiting. So it has a slightly more attractiveness at some tiny little spots, and where the neutrons are, there's obviously not as much attractiveness, so there's a slight bit of less attracting force. So it's going to wobble, and it's going to create this blur that we see. That's because the blur is extremely bad camera work. That is all. If you were to slow it down and properly visualize it, you would be able to see the electron orbiting the atom as it is, in a very basic film style like thing. You would know what it is, how it is, and how just one of these pixels could be where the electron is. Okay? That's how that works. Any one of these pixels is the electron. But the point is, okay, that it's moving at it's moving at an insane speed of a quadrillion spaces per second. A quadrillion of these atom sizes per second. Now, the moment you start working with something like a uranium atom, which is much bigger in contrast to a hydrogen atom, like 5 times or more bigger, just in the radius alone, you end up with a very weaker amount of attractiveness for these electrons, and so those outer layer electrons have a way more predictable pattern than you might think. There's a very limit of what they can do. And so Bose-Einstein condensate, freezing something to a very low temperature, you're going to end up with the atom itself not having a lot of motion, but the electrons are still going to be moving around. But when you start to lower the motion of the atom itself enough, and the electrons start to make these pairs, and you know why that happens? It's because the reason why the electrons form pairs is because the positive end, it's just like batteries. The positive end of one electron is flowing the electromagnetic field to the bottom end of the other electron. It flows like a torus through itself and around the outside. The only way that you can flow consistently, okay, is if you make pairs, and those pairs are flowing from one into the other and around and back again. That's how the electromagnetic field can have an equilibrium. It's hard for it to form a triplet, although it is possible to do that, and that has an even more interesting physics situation. But it becomes less possible for something like, for example, a quad electron. Like 4 electrons, it is possible to maybe work in a circle, but it just doesn't. The electromagnetic field doesn't want to flow in regular circles like that. It wants to flow in a torus, and lining up those toruses is not going to work with just 4. But the bigger that area is, the larger number of electrons you add to the system, the more likely it is that you could make a ring of electrons that are basically just one electron, end to end, like a set of beads on a necklace, going a perfect circle, so that all the flows are inward and outward. All the magnetic fields just flow on the outside in a circle, and all the electromagnetic field on the inside also flows in an opposite direction circle. This is a really crazy scientific stuff that no one's talking about because it hasn't even been theorized enough to be in a paper that I've ever heard anyone mention in the history of ever. No one talks about that. But that's because they're not thinking about electrons as a particle interacting with the electromagnetic field, as a liquid that's flowing through it, being pumped by it. And the faster you move an electron, the more it interacts with the electromagnetic field at a time, so the bigger impact and the larger the electromagnetic effect becomes. The wider the area is that is able to be reached with the electromagnetic field. And I would love for people to understand how electrons work. But they come into this YouTube space, they think that they know what they're talking about, they say stuff like Einstein boson condensate, they say things about superposition and supercriticality or superconductors and superfluids. And it's interesting about the fluids, that's not a lie, and it makes total sense that the more you have the electrons be able to flow like that, with their temperature being exact, and that loop happening, it's a more condensed and more simplified electromagnetism situation. So that's why it also works with, guess what? An even number This is what happens. They don't even realize it's an even number of electrons creating this. If you have that same even number of electrons on a bigger atom, you can make a superfluid out of that. But they're not thinking about that, because they're not thinking about the geometry of electrons.
Possible to know all properties of a particle, so it's more realistic to think of it as more of a vague blob or tiny cloud, or a little wave packet. Because in quantum physics, particles are waves, and this wave function is where we more...
Okay, no. 1,000,000,000% no. Particles are not waves. Particles actually have a physical presence that they exist in, a state of being which is a physical matter. You fire an electron at that detector, you're going to get a little dot, and that little dot is the electron hitting it. It is a dot. It is a bead. It is a tiny bar magnet. That's how they are. You can't say they are waves, but that's because you don't know any better. And I'm sorry that you don't know any better. But that's just how it is, and I'm not going to beat around the bush about this. This video is saying a bunch of false information based off of literally over 80 years of dogma. Like, people freaking just talking so much about the double slit experiment, they don't even understand that electromagnetism is a fluid on the very smallest scales. So, you wonder, what is electromagnetism actually? Some people have stated that electromagnetism must be photons. And for a while, I debated in my head, are photons the actual means of electromagnetism? So when you shine a light at an atom, you have a chance of bumping off that electron you have the chance of bumping off the electron, called the photoelectric effect. So there has to be something about that. But the thing is, the photons have not just a straight motion, but because of their frequency, they literally have a sideways motion. The heavier the sideways motion, or the more compressed the frequency, like right now if it goes wobble, 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 that's a really small frequency. It doesn't wobble very much. It just goes woo like that. But if it goes, it's punching back and forth really fast like that. And that punch is what does it to the electron to get it to kick out of the shell that it's in around the atom, and it just shoots off. Right? That's what's happening. The sideways part of the photon is what's making the electron jump off.
More or less expect the particle to be. Its true position can never be known with 100% certainty, so the best approach is to imagine it as a cloud or a wave of probability with its own energy.
You know, if you do that experiment where you bump off an electron, you know exactly where it was. No one can ever know the present tense of anything because your senses already have lagged behind. You're nanoseconds away from knowing the now at all times. You will never reach it. It will always be the past that you're witnessing. So saying we don't know where things are is irrelevant. What you need to say is we don't know maybe how to simulate or how to imagine where the particle would be, but if you do a bit of like just shine a light at the atom and the electron shoots off in one direction, you know where it came from, and you can reverse engineer that to know where it's been to a degree.
The identity. If you find this impossible to wrap your head around, that's just quantum physics for you.
No, it's not, unfortunately.
So, if we cool the atoms in a cloud of gas way down into the nanokelvins, their energies start to approach their lowest point, and these little wave packets grow bigger and their wavelengths become longer. Now, at about 50 nanokelvin, these waves start to overlap and blend into each other, and they start to behave as if they were one big atom. They don't become solid, to be clear, it's just that all these...
Okay, listen, no. Again, the problem is you're still... Of course, this is going to happen. It's the same person. They're still talking about waves. No, what you don't understand and what you're not talking about correctly is that all of the different energies that are binding the atoms, because their momentum has gone to zero, almost, they don't bump against each other anymore. So compression is able to happen to the point where they almost occupy, and they never occupy the same space, but they end up, basically the only other thing that ends up moving is the quarks inside the protons and neutrons. They're still moving. So unless you make it so that they disappear and turn into just a sea of quarks, you haven't slowed it down enough.
Atoms lose their individual energy identity, and you can't tell one from the other, and so they condense into this single collective quantum wave. A Bose-Einstein condensate is effectively a different state of matter from solid, liquid, gas, and plasma, but it's probably only possible in laboratories because we don't know of any natural circumstances that could cause it. As such, it could only...
I mean, if you could make a cold star, that's pretty much how you do it. Cold stars are basically the concept of there's gravity, but then there's no heat. And you know why? Because somehow, okay, imagine all the mass just wasn't able to keep moving. Like, let's say somehow let's say you stripped all of the electrons off of the mass. Like you have in a neutron star, it's mostly just neutrons in there. So you could end up with, there's a theorized about this extreme fluid that's inside called strange matter. And it's freaking weird that there could be inside of a neutron star, if it were to be even more dense, even bigger, and more compressed, the inside of the neutron star is either a black hole or it's this strange matter. And strange matter is weird in the fact that it's quark soup, and it's even weirder than that. And quark star is not even a thing people talk about being even possible, but a cold star would be, yeah, basically everything has, it would be the center of a star that has compressed so much. Besides neutron stars, it is the most dense thing, but also isn't hot at all, somehow. And, like, the star has somehow attractiveness to it, but there's no heat, there's no rotation, there's no movement. It doesn't even move through space. It's just a lone white dot in, it might not, no, it wouldn't be a white dot in space. Is that what a black hole is? A cold star? Because it doesn't emit light, you know? So, would a black hole just be a cold star? One that's actually reached absolute zero. It doesn't emit anything because there's no interactions happening. Because it's literally just, like, going so crazy in there that there's nothing but pressure, there's nothing but substance, there's nothing but something. We don't actually know We don't actually know. There's no evidence. There's no, like, someone's done a scan of it and everything and figured out what it is. We don't know what the heck's in a black hole. None of us know. So, cold star is a nice theory. Also, I've never heard of a cold star as a theory. So, Nobel Prize for cold star. Come on, that can't be. I can't be the first one to think of a cold star.
Made in very small amounts, and so it's very fragile. Any interaction with anything outside of the extremely cold environment would break the condensate and turn it back into a normal gas. Just so you know, superconducting materials and superfluids are also different states of matter outside of the four most common ones.
Yeah.
The Bose-Einstein condensate was predicted in the 1920s by Albert Einstein based on the work of Indian physicist Satyendranath Bose.
Yeah.
It wouldn't be until 1995 that this exotic state of matter was created by a group of scientists under the leadership of physicists Eric Cornell and...
I mean, it's true that Bose-Einstein condensate is really neat and everything, and how it's made and things, but it's not about... The problem is when you get convoluted and you say something like the frequencies are interchanging and mixing and everything, you're forgetting it's still a substance. It's a blob. It ends up becoming a blob of indistinguishable substance that all of the different what's the word for it? The shells of the electrons are... Have they combined enough? Like, do they just become... Do they start sharing... Like, at that point... Like, it's not that... Here's the thing. And this is what they said. She just said it. If you heat it up again, if there's any interaction, it turns back into a mist, into gas, and all that. It reassociates. It is always. Here's the problem: you cannot say that it becomes this frequency and then it separates again, because the distinctness of all the parts become what they originally were. They're now separate again. So you can't say it becomes this interlocking frequency and all of that. That's ignorant. You literally have bamboozled yourself in this.
Riemann. They received a Nobel Prize for their research in 2001, along with German physicist Wolfgang Kepler, who also made a Bose-Einstein condensate just a few months after the first one was made.
I don't deny that.
Research into this is important to help us understand quantum physics better. It may be helpful in developing nanotechnology.
Recently, and I'm always pissed off at this guy, but I saw this. Don't put liquid nitrogen in a... Did he say Stirling engine? My guy.
This is a steam engine called Hero's Engine. Whoa.
Don't put liquid nitrogen in a Hero's engine. That's what you should have titled it. But the point is, liquid nitrogen trying to go out of those little holes will create that amount of thrust. As long as he's not like faking it with some stupid little magnet rotary thing and he mixed up the audio somehow, which would be annoying, and I'd be pissed off at him for false advertising, false labeling science, because I already am pissed off at him. But it just in a lot of freaking reasons. The thing about this, right, it's basic. You heat up the stuff on the inside, the pressure increases, it pushes out the only way it can, and it starts spinning. So, as long as there's stuff to go in, right, then it can constantly go out. And the problem that you don't have, the problem you have with one of these situations is that you don't have a way to put more into the system because you're a bad designer, I guess? Because, like, you can make a system that keeps on eking in more stuff. So the Heroes engine can work infinitely, as long as you're able to then
There it goes.
You heat up the bulb full of water, and the water steam shoots out the spouts that are all aimed in the same direction. But what happens if you put liquid nitrogen in it instead of water?
Okay.
And here's the thing, you can get nitrogen out of the air, so what if you could just cool the air with the power from this, and then pump it through a tube at the top that flows into it, so then, and make sure that you're using like a one-way valve so it can only go in, and as the pressure releases from the Heroes engine, it would then suck in or allow, like the way they use with regular steam engines, they use the pressure of the engine to force more steam into the engine, or more water to turn into steam. It's a self-regulating system. It's beautiful. I love it so much. Just do that with a Heroes engine. You're not even using heat at that point. You're using the heat of the air around you, because
Completely filled with liquid nitrogen now. Whoa. It's working.
So the thing about liquid nitrogen and that is that its temperature is so low compared to the temperature of the atmosphere. It ends up expanding so much faster simply by the room temperature. So as the main problem with this is the icing effect, where the tubes of it could end up getting clogged by the ice itself. So unless you have a way to make it so that the tubes don't freeze over, you're going to end up with constant flow and amazing speed. I don't know how much power this engine could have.
Holy cow. This is so fast. Oh crap, I can't stop it.
This is a steam engine.
So here's the thing, right? Yeah, a couple things can happen. They can get so stuck. Now, the thing is, you want to have the diameter of it to be a certain size so that it can constantly go out at a pressure that can also make a force. And here's the thing, if you try to make it bigger, it really doesn't work so nicely, because the amount of force that you can apply from any given tube, no matter how many tubes you were to put in, at the size of it, you would have to have tons of tubes. The bigger you go, the more tubes you need, and if any of those clog, you end up with a lack of power, and it's just really not practical, but it is really interesting. Moving back to the video.
May be helpful in developing nanotechnology and quantum technology, and in studying the nature and behavior of black holes and neutron stars.
Okay. Let's go back to the idea of Einstein condensate. You're never going to use that in nanotechnology. Shut up. I'm sorry, but no. Not even remotely gonna correlate those two situations. That's not gonna happen. I'm also not subscribed to her, but I don't remember if I've ever heard of this person before. It's like the gobbledygook lady. Who knows what the heck I can expect from this person? But they talk in video. They talk in ideas such as the electrons behave like a wave, or they are a wave, as if it's a fact, which it's not, which upsets me to just no end.
May even be useful for research into string theory, which hopes to unify the theory of gravity and quantum mechanics into one big theory of everything.
Okay, you want to know the theory of the very small? Besides the fact that electromagnetism is a fluid, at the very smallest layers, even smaller than electromagnetism, if you can imagine that, electromagnetism is basically like if you have, like, you can't think of, okay, let's say that you somehow were to think of electromagnetism as a large scale thing, right? You got the little electron, and light is passing through it in a torus, so it goes in and out, circle, in and out, circle, and it does that constantly. With the electron, that's what the photons are doing, supposedly, in a constant loop, in a torus. This is the electromagnetic field, right? This is what's happening all the time. But you end up with two electrons next to each other. Suddenly you have the field going in one, and then around itself, down, and then in the other, and around and down. The only way that it works is if you have this cycle. Well, actually, listen, I'm not going to lie. I'm wrong when I say there's only one way that it works. There are two ways that it works. Both of them face up, and the electromagnetic field goes in from the same direction, or it goes in one direction, out the other, like batteries. One is in series, one is in parallel. That's just how it works. That's how flowing electromagnetism works. It can flow on the outside, and then they're in parallel, or they could flow into each other in series. Does that make sense?
One of the coolest things that a Bose-Einstein condensate has been used for is slowing down light. The speed of light that you often see and hear about is the speed it has.
You know you can do that with a lot of substances, right?
In a vacuum. But many substances, like regular old water, for instance, slow light down a little bit, at least from our point of view. From the point of view of the photons themselves, they always keep going at the same speed. Weird, yes, but that's just special relativity.
Now imagine you have the Bose-Einstein condensate. It's basically as thick as matter can get. So you're not talking about individual atoms with any space in between, so the photons themselves aren't able to really bounce around in there. So they either bounce off of it, or when they go in, they kind of bounce around forever. Like a really long time. Like a crystal.
So, in simple terms, a Bose-Einstein condensate can be made more opaque or more transparent by changing its frequency by pointing a laser at it. If you then change the condensate's frequency at the same time you send a light pulse through it, you can...
Again, I'm really disappointed. It's not frequency, it's lattice structure, and shush. But
slow that light down, and you can even stop it completely. This is what Danish physicist Lene Hou did at Harvard University in the year 2000, and the year after, she and her team effectively stopped a light pulse inside a Bose-Einstein condensate. The important part here is that this experiment shows that it's possible.
I mean, the light went in. It had nowhere to bounce out from, so it was just in there. It's not stopped. It's like, okay, I have recently saw another clip. You're gonna love this, because I love this.
What I have here is just a regular ball bearing, and when and it was honestly even anything weird would happen if I tried bouncing the ball between them. boson.
That is really the coolest thing I've ever heard.
Honestly, even better than I expected. I mean, I assumed that it would bounce a lot, but not nearly this much, and this...
I mean, those plates are made out of some weird metallic glass, and the ball, it's kind of really metallic rubber, sort of. I don't know. Not really. I don't know. But like,
super high-pitched sound that it makes tells me that it's bouncing a ridiculous number of times.
yeah.
In fact, at its peak, at least based on what I could count, I could sometimes get it to bounce up to several thousand times per second, which in my
that up and down sound, dude. Play it again.
sometimes get it to bounce up to several thousand times per second, which
That sound is awesome, dude. This is why I love science. This guy's practical as frick. I love it. He's the best. I knew that the bouncing thing was cool. This is cooler than the bouncing thing on itself because, I mean, obviously, you're getting constant, immediate feedback. Like it bounces like the friggin' crazy thing. The fact that it goes in and out like that, just
which in my opinion
it goes up and down with that frequency because of the amount of space he gave it. He gave it a little bit extra space so it could bounce a little longer. That was fun. Now, thing about this, okay, let's go back to the video. Alright, so...
The important part here is that this experiment shows that and the year after, she and her team effectively stopped a light pulse inside a Bose-Einstein condensator.
Pretend that light pulse is that bead, and instead of the two plates, we have a Bose-Einstein condensate. That's what's happening. It's bouncing like crazy in there, only it has nowhere to go. Okay?
The important part here is that this experiment shows that it's possible to store information in this brand new way, and that makes it extremely interesting for the making of quantum computers. As it is, quantum computing...
Okay, no, oh god, no. Oh god, no. God, no. Let me explain why. In order to change a single bit, you have to freeze it to an insane temperature, and in order to let out that bit, you have to change the temperature. How fast can you do that effectively? Not fast at all. You can't. To get it to that temperature, you have to wait way longer than nanoseconds. Guaranteed. Trillion%. I say that a lot, okay? I don't care. I really don't care. Dude, fuck no. This bullshit about, oh, you could use it as a quantum computer component. You will never use this as a quantum computer component. Because it's just not practical to speed. Like, maybe you could just do tiny little zaps, and that's still you putting an input and then releasing the bit. The information you store may be really tightly compact so that you're storing stuff, but guess what? If any amount of energy goes into that, like a cosmic ray or anything, it's gonna release everything, scramble everything, it'll be ruined, it'll be useless, you can't do anything with that. A goddamn, it's just not reliable. A neutron, or a neutrino. Neutrinos go through the Earth all the time, thousands of them, through your body every second. You don't even notice it. But neutrinos, really tiny, near the speed of light, tiny bit of mass, except not really, and they don't interact with anything, pretty much. So, like, If you were to imagine yourself being ripped to shreds nanoscopically, that's what neutrinos are doing, only they don't actually feel like anything. They don't do anything to your body. You're still intact, but they're still ripping right through you like you don't even exist. Because they don't care. You might as well be miles away as far as they're concerned, because they're so freaking tiny. It's crazy.
It's technology that's still in its infancy, but new discoveries are being made all the time.
Yeah.
So who knows what the future will bring. Thank you for watching.
No.
I hope you learned something new today, and I will see you soon.
Unfortunately, I unlearned a few things, but whenever you talk about waves, I need to remind myself, Simon, no, that's not how quantum mechanics works. It is not waves. It will never be waves. It's never been waves. Let's go back to the beginning of the video. What does she say?
Absolute zero. Minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit, and the 0 point on the Kelvin scale. The point where there is no more energy in a system. The absolute coldest anything can be.
She never once in this whole thing talks about a sea of quarks. And then you have to go even smaller than that because quarks are not fundamental. Shut the fuck up. Quarks are not. Okay, look. If you don't know anything about quantum mechanics, let me school you a tiny little bit right now. Quarks. Okay. Everyone knows how atoms work, okay? You got the protons, neutrons, electrons. The protons and neutrons are made out of quarks. Up and down quark, you got the mixture of the two, you end up with one of them is positive, the other one's negative, the electron's negative, and the other in the atom is neutral. So, generally speaking here, okay, you would think that would be the smallest thing possible, but the shell of the atom is a thing. That's not made of quarks. That's made of something else entirely. The Higgs boson is a tiny little energy difference on a graph. It's slightly higher than everything else. It's what's said to give everything its mass. I would say mass, yeah, never mind. I'm not going to get into that right now. But the point is, when you go to the electrons, and then you have stuff flowing inside of electrons, you realize electrons being the same as fundamental particles is a joke. Because the electromagnetism is even smaller than that. And then you realize photons, normal visible light, works with electromagnetic energy. Meaning photons can't be the thing that transmits the electromagnetism. Photons are tiny little dots, smaller than electrons. They ride electromagnetism. They can be turned completely into a quanta we call a photon. Now, the frequencies of light, the fancy thing about that is that they're basically like an object that is a sine wave. In three-dimensional space, they are a corkscrew device that is flowing through space at a regular interval. Now, if you think that the electron being a pump of electromagnetism is fancy, you have to realize that the electron is made out of components that are able to actually manipulate the electromagnetic field and light and they are able to do all sorts of things. Like, it's interesting how you wonder why galaxies and the outside areas of things will bend light. Well, it's really simple, isn't it? Like any prism, the light is bouncing around inside of that structure. So even if you say you have slowed down this Einstein condensate and then you have a photon inside the Einstein Bose-Einstein condensate, I don't know about you, but the picture of a photon next to this condensate doesn't match reality at all. Because a photon is smaller than an electron in reality. And the condensate was only slightly bigger. And the condensate is made out of atoms, which are way bigger than an electron. So how can a photon look as big as hundreds of electrons? It's because it's not an actual photon they shot into the Bose-Einstein condensate. That was no photon in that picture. There's no way. The size doesn't match at all. Unless, of course, the thing that you're visualizing isn't the actual thing itself. You're saying you took a photon, you stuck it inside of a set of atoms, and I'm here to tell you that's not what you did. Where is this experiment? Yeah, this thing. This is not a proper representation. How did you get this supposed picture? First of all, right? So what you're actually seeing is like a heat map of the stuff. It's the infrared radiation of the Bose-Einstein condensate and the photon itself. The photon is not that size. It is way smaller. It emits heat. The heat is still coming out of this, which means it's not perfect, or it's just a simulation. One way or another, this is not a correct representation of what's actually happening with this, and I'm pissed off.
This is what Danish physicist Lena Hau did at Harvard University in the year 2000, and the year after, she and her team effectively stopped.
Yeah, that's a heat map. If you notice,
transparent by changing it, and you can even stop it. Stopped a light pulse inside, light down, and you can even stop it completely. This is what Danish physicist Lena Hau did at Harvard University in the year 2000, and the year after.
Okay, so let me explain to you what this map really looks like. This is a simulation. There is nothing. I would love to read more about this specific experiment and to know what the heck is happening, and to have it be that she's interviewed by somebody and they explain it in detail. That video, yeah, I would love to see that. That's real science. I would love to see real science. That'd be great. This representation, if I'm not mistaken, is like a heat map. Again, if the photon is looking like a blur like that, you can tell that the shutter frame is going at, and it cannot be obviously as good as light speed, to be able to, like, you can't slow it down fast enough to actually see it correctly. But this is probably shutter speed. Like, you have to understand, the other photon is going by at the speed of light. Okay.
She and her team effectively.
So if that thing is moving at actual speed, like, the stuff around it must be slowing down light incredibly. So, okay, I'll give you that. Maybe you slowed down light around the substance, and then in the substance you were able to catch the thing. I can accept that. That's not impossible, okay? It's just not, it's not in the realm of complete, it'll never happen. It's just, there are details missing from this representation, is what I'm trying to say. Okay, let's go back to the very beginning. Because I'm pissed off still.
Humans.
No. Further back. This.
The point where everything, down to the tiniest particles, stops moving. Well,
I mean, the fact that you were able to make a photon basically stop moving, I mean, relative to the rotation of the Earth and all that jazz, shut up. Nothing stops. But doing that, yeah, it's kind of pretty cool, pretty amazing. Love that. So the idea of absolute zero involves not even moving through space. We can't accomplish that on Earth. We're moving through space. So, yeah.
that's how it would be in classical physics, but it's actually not possible to ever reach absolute zero. So why is that? Temperature is our way of measuring the kinetic energy of particles in matter. The faster atoms...
I mean, if you think of the thing not moving relative to everything else, then, I mean, there are ways of going to absolute zero if you're considering yourself, you know, moving relative to, like, a photon moving through light, through empty space. Compared to that, you might as well be moving still. But are you? No. It's the same difference.
vibrate, the higher the temperature is, and temperature drops when atoms slow down. Logically, once atoms stop vibrating entirely, that's the coldest matter can be, so that is absolute zero. This works within the framework of classical mechanics, the collection of mathematical theories that began with Isaac Newton, who first formulated the laws of motion that describe how things behave.
I'm sorry, Galileo, anything to you? We got people, never mind.
Behave on the macroscopic scale, from planets to stars to humans and our machines. In the beginning of the 20th century, physicists discovered that these theories were no longer sufficient to describe and predict what happens on the very smallest scales, on the atomic scale and beyond, down into the world of elementary particles and quantum mechanics.
Okay, I would love to ask you, what is this? What am I looking at? What is this representative of? We don't get an answer. It's some BS thing that's like, oh,
Theory in physics
this?
that aims to describe how
What is that? And that, yeah, I don't know what this is supposed to be.
matter and energy behave on the most fundamental level. Quantum physics tells us that even if the lowest temperature possible could be reached,
It's a
particles will
sparkle.
always still have some kinetic energy that cannot be removed, and this is called zero-point energy. This arises from the Heisenberg uncertainty principle.
I mean, do you even talk about quarks in this video? Seriously though.
Which states that you can never be entirely sure of all properties of...
This is the point when I typed the word no.
any given particle. For example, if you try to measure the speed, or rather the energy of a particle, you can never be entirely sure of its position. If you measure its position, you can never be entirely sure of its energy.
You know what? That doesn't fucking matter. You can know where a thing... The reason why... Okay, listen. The reason why people say something like this, why the uncertainty principle exists in the first place, okay? Heisenberg. The reason for it is because like as I say, if you have something, a still image of something, you can't tell where it's been or where it's going. You don't know anything else about it. You just know where it is right then and there, right when it was there. When something is moving, you have no idea where it is? Question mark? Well, that's not true because you can predict where it is. A lot of what we do is predict where things are. We don't, again, you don't even, like, the only reason why you're able to move your hand around is because when you moved it, your body is still sending signals and your hand hasn't moved very much relative to everything else. If you turn off those signals with some ketamine or something, don't ask me how I know. Well, actually, it was during I've had one ketamine experience. It was a procedure that knocked me out completely, and it basically had me not know where my body parts were relative to each other. So I didn't know how much force I was applying when I was trying to move. So I had to move slowly because I didn't know how much pressure, like when you say push down with your hand, I couldn't do that consistently, reliably, without just launching across the goddamn room. Because I can't feel pain. I can't know where my body couldn't tell where anything was. The only thing I could feel was maybe some pressure, and that's about it. I couldn't actually tell how much force I'm applying, so I have to move slowly. The doctors were hilariously baffled and not understanding, and they say, oh, it makes you move slowly. I'm like, do you want me to move fast? Because I can just jolt right now. There's nothing that would be able to stop me. The feeling of pain being gone and the feeling of lack of sense, like I would just be able to hyperspeed and I would ruin my body doing so, probably bash against the wall really fast. But I wasn't slowed down because of the drugs. I was slowing down my body, my conscious mind was making me slower because I wanted to be careful. Never mind.
And so particles always sort of vibrate a tiny
Why was I talking about ketamine?
little bit, even in their lowest energy state. I know that seems counterintuitive, but that's just quantum physics for you.
It's not.
The temperature of space itself is about 2.7 Kelvin. And this is because the space between...
Okay, so... First of all, I don't even know if she mentions quarks. I don't remember. I'm not watching it again. The video is already too long. Watch it yourself. Tell me in the comments the timestamp in which she mentions quarks, and I'll make a response video. That's how this works. We talk to each other on the internet all the time. You and I. Why would I read her name? I thought it was Blue Toddler. That's just... It's... OT Dweller. Okay, whatever. Anyway, the point is, if you want to take away anything from this, alright, first of all, if you want to take away anything from this, remember these things. Electromagnetism is a fluid. Don't ever forget that. Electrons are never a wave. The electromagnetism works like that. That's why people are so confused about the double slit experiment. The electromagnetism makes the waves and the interference pattern. The electron goes through the corridors of those waves. It doesn't interact like a wave. It never has been a wave. It is always a particle. That's what we can come out of this with. And if I were to make that into the only part of the video, you would, there's just so much I had to talk about. Holy crap, I couldn't not talk about it. I can't. It's not possible.
Stars and planets and clouds of interstellar dust and gas does not hold a lot of particles that can interact with each other and heat things up. The average density of the universe is about 6 protons per cubic meter, and since that's an average, interstellar space between stars and cosmic clouds is even emptier and colder. The reason space itself still has a temperature a few degrees above 0 Kelvin is because of the
So is a nebula a cold star?
Cosmic microwave background radiation, the leftover glow of an event called the last scattering, that occurred about 400.
Okay, hold on. When you talk about the cosmic microwave background radiation, and then you show basically the surface of the sun, this is not how anyone has ever talked about. Let me just show you the CMB really quick. Yeah, it looks like that. This is one of the images you constantly see. This is the other image you constantly see. Look at this shit. This is what you see. You don't see this. So you fail.
1,000 years after the Big Bang itself. At this point, the universe stopped being an opaque soup of particles bouncing around, now that its temperature had dropped to about 3000 Kelvin. And so it was cold enough that electrons could bond to protons and form hydrogen atoms.
You mean warm enough, right? Because if the Bose-Einstein condensate is homogeneous, then that means the beginning of the universe wasn't hot. It was cold. Could the beginning of the universe been a Bose-Einstein condensate? Just the entire universe be that cold and be that homogeneous? The answer is no. Is what most people would tell you. I'm not so sure. I'm actually not sure right now because I postulated the question in my head and then I said it out loud. And here we are. Bose-Einstein condensate at the beginning of the universe. Put it on a sticker. Get people thinking about it. It doesn't matter if it's real or not. Theories are meant to be mentioned. Doesn't matter if it's real. Doesn't matter if that's what actually happened, because I don't know. But, I mean, you think about it. And if everything's homogenized, now here's the thing, right? If it was homogenized, if the universe started as a Bose-Einstein condensate, then it means it still was structured matter in the beginning. This is what everyone keeps on saying. What made it structured in the first place? What made the quarks happen? You know what really happens with quarks? This is going to blow your mind. You take a quark, and another quark. They come in pairs, right? You put in enough energy that they separate. Suddenly, each of the individuals, like quark A and quark B, make a quark B, make a C and D, so you end up with 4 quarks at the end of it. You don't end up with just the 2, you end up with these other 2, which are the pairs now. And if you separate those, then you can have 8 of them. And you can continue doing this, and you could just make matter out of basically nothing. The ether. Where's that coming from? The same stuff as virtual particles. As I mentioned in other videos, and I mentioned basically all my theories in every video I ever say. This is not very cohesive. Any given video is a goddamn essay of my entire existence of understanding. Not really. I know way more than what I ever say in these videos, which is crazy, because I'm already talking for hours. But the thing is, you can just make matter separating these quarks from each other. So what if... Oh, I was talking about... sorry, I lost my train of thought. It was talking about virtual particles. What are virtual particles? In space, in the basic electromagnetic field and everything, even smaller than the electromagnetic field, there are these other more fractal. They're not fundamental. Fundamental is a word that means the lowest level of our basic, the atomic structures. Going lower than that, we're starting to work in not fractal, fragment components. Stuff that is basically just the tiniest essence. It's not photons. It's even smaller. And these tiny bits, at some points, will cross paths. And at these intersections where one's going one way and the other one's going the other way, and they meet at one point, virtual particle. The moment that they continue moving on their way, virtual particle's gone. Disappears like it never was there, because it never was. It is two different things interacting with each other, constructively interfering, leaving. Boop. That's it. That's all they ever was. That's a virtual particle. These things are also the components that turn into the quarks when you separate them, and then it turns into matter. The quarks have the binding energy. Interestingly enough, what is going on with quarks and their binding energy, the strong nuclear force? What's up with that? Well, they say it's photons working in there as well. Some other boson that is gluing them together. It's interacting with them. Like the Higgs field and all of that. It could be that there's even smaller stuff flowing through these things. Anyway, this picture is insane.
This stopped electrons from endlessly scattering light, and so photons could travel freely, and this radiation is still detectable as the cosmic microwave background.
So look. Again, this is the this is the picture of the cosmic microwave background as people say it. Right? That's what they say. This is what people see. Based off of like the same idea of if you look at a map and you look at like just this energy pattern. That is a really good picture of the CMB. It doesn't have any of that heat mapping, like encoding BS. It's the pure information. Who is this? I don't know you. Interesting. So, why is there this kind of picture and I never see this? And then there's the colored picture, which is what I always have seen. And it just looks like a picture of Earth, to be honest. And then you have her picture, and it's goddamn this yellow shit. Looks like the star.
The leftover glow of an event called the last.
What is that? That's just the surface of the star. That doesn't look like the CMB to me. It looks like an idea of what the universe maybe looked like when it was starting. I guess that's what she's
scattering that occurred about 400,000 years after the Big Bang itself. At this point, the universe stopped being an opaque soup of particles bouncing around, now that its temperature had dropped to about 3,000 Kelvin, and so it was cold enough that electrons could bond to protons and form hydrogen atoms. This stopped electrons from endlessly scattering light, and so photons could travel freely, and this radiation is still detectable as the cosmic microwave background. The coldest place in our solar system is surprisingly on the moon. There are craters at the moon's poles where sunlight never reaches the bottom, and so the photons. It's believed most long-period comets originate here, with their orbits of 200 years or more.
Have you heard of electric comets? They're comets that literally, because they're moving through space and interacting with stuff, there's like static electricity. It's made constantly and discharged constantly, and that's the comet tail, not actual like some ice plume or something.
Now, because the Oort cloud is supposedly made up of trillions of small, cold, and dark objects, it's currently pretty much impossible to determine its size and overall shape, and it seems only loosely bound to the Sun. Other stars and the gravity of the Milky Way itself probably disturb the cloud and pull objects out of it all the time, especially from the outer regions. The cloud may extend as far as halfway to the nearest star to the solar system, Proxima Centauri, which is about 4 light years away. Temperatures in the Oort cloud could be as cold as 5 Kelvin. The coldest place that we know of in the universe is the Boomerang Nebula, at about 5,000 light years away from Earth. It's formed from the gas ejected by a dying sun-like star at its heart. Now, this star is expelling gas so fast it expands and loses heat and cools down so quickly, its temperature has dropped to only 1 Kelvin. This is colder than the surrounding cosmic microwave background. Cool. The only places in the universe we know of are even colder are laboratories here on Earth, where scientists have managed to cool matter down to only 38 picokelvin. And
this number is insane. This number right here, that's crazy. It's like a fraction of a fraction of a fraction.
Yes, that's a 0 with 12 digits after it. So why are scientists doing this? The idea of an absolute minimal temperature goes way back to the 1600s, and since then scientists have fine-tuned ways to account.
I mean, basically, if you can make something cold and then colder, you think about it hard enough, and if you know about atomic stuff, then you understand about how it's just the wiggling and all that, and if you can stop the wiggling, then you can make the temperature as cold as you want.
Calculate absolute zero, but they've also been trying to cool materials down to as close to this point as they can. By 1845, Michael Faraday had managed to cool and find the temperatures at which most known gases at that time would liquefy. Now, Faraday is mostly known for his work, but
thing is, I should actually have the entirety of her video, which I didn't. I skipped over some very small bits, and what is the proper format for a reaction video? Because I am well beyond like a standard essay. At this point, we're in a lecture for ages, going into all sorts of things. I gotta admit that. Anyway, so yeah, this is my reaction to her video, where I will take this information, put it into the link in the description of the video, live stream as it is the currently thing. Where's my stream? How do I find my stream? What? How do I... Okay, whatever. I guess I'll be able to edit the description later, so I'll have the link in the description for this video. Whatever. No, I'm not gonna forget. Trust me. Like, I can put it in, like, the comments of this video. Anyway, if you need to find the video, like, there it is. But, again, fine. I'll consider subscribe. What is this? What is a Planck star? I mean, that's neat. Do you talk about cold stars? Is the sun not on fire? The definition of being on fire is that the thing will burn, and yes, it is. What the fuck do you mean it's not on fire? It's a goddamn Roman candle burning out and spewing out energy constantly. What do you mean it's not on fire? Oh, shit. I'm subscribing simply so that I can make more reaction videos, because I just already am starting to have bad vibes about this. Like, come on, man. What am I working with here? That's weird. You don't have a lot of videos. That's cool, I guess. You can only do... Wait a second. What? Wait, so that's Strange Stars, and then you go into this months ago. What was your most recent video? A month ago. Makes sense. Stunning beauty of newborn stars. I mean, they are very pretty. Not gonna deny that. I mean, if you consider a puddle of gas coalescing into a glowy ball pretty, then of course they are. They're really beautiful. When I saw a newborn star in Magic School Bus, I was like, that is really cool. It definitely was a sped up idea of the concept, and it was like, that is beautiful, that is majestic, that's friggin' awesome. I will never say that it's not pretty. It's damn pretty. Like, it's also really shiny and stuff. Like, it shines like friggin' neutron star, or pulsar or something. It's like when it ignites from, like, just the moments before it starts being a star, and then boom, it's a star. It's like, there is that moment. It takes place, and it's like friggin' light bulb turning on and stuff. Only it's a star. Whatever. Anyway. I need to sleep. I think about the implications of diving in too deep into the stream by this channel, other people's channels, people talking about quantum mechanics and let's just be real here. Stirling engines were misrepresented by Bill Nye. I have respect for that dude. I can get into that in a different video if I haven't already.